started recording a little bit late, but this is 3:30, and we talked about some starting assumptions that we're talking about with evolution. We're talking about sources of evidence for evolution, and the fossil record is our first source. Okay, so what fossils show and what they don't. Fossils, and I'm going to read this, and then I'll shut up while you copy. Fossils do show hard-bodied organisms, or those with skeletons, and they show woody plants. They show a geologic time of death. What they don't usually show is soft-bodied organisms, things from grasslands, deserts, and mountains. So based on the fact that we're saying right here, do all things leave fossils? No. You're never going to find a worm fossil. You're not likely to find a cactus fossil from a desert. Bacterial fossils are incredibly rare. The stromatolites that we talked about that are the earliest fossils really are only present because of some weird aspects of how those things arrange themselves. We see organisms that have shells. Those leave fantastic fossils. Fish skeleton fossils. And you had said you had a fish fossil. Those are pretty common. We have fossil snakes, we have dinosaur fossils, we have early fossil birds, but we don't get fossils from all organisms, and we don't get fossils from every place on the planet. Somebody had asked this, and you guys have got fantastic questions about this. How can you tell how old a fossil is? And there are actually forms of chemical analysis that we can do when we find a fossil, and we can date a fossil usually to within a few thousand years of age, which doesn't sound real good, but when we're talking about millions of years, that's pretty good. If you can get it to within a few thousand, that's pretty good. So fossils don't show everything, but they do show a lot of organisms. We have a lot of fossil evidence that shows us forms of organisms from the past. Okay, so what? We have fossils. Great. Woohoo! I'll read this and then I'll shut up while you copy. You can calculate the geological age of the rocks, and then the fossils can be arranged by their ages. And something important to know here is that rock layers tend to form with newer rocks on top and older rocks on the bottom. This is called law of superposition. Fossils show evolutionary stages. So we can put together a fossil lineage, a line of descent for fossils that shows evolutionary stages for an organism. Okay, so I said that we can chemically analyze a fossil itself to tell how old it is. There's a catch. That only gets us back so far. So for fossils that are older than we can do carbon dating on, what we have to do is actually figure out how old the rocks are. And that's not as hard as it sounds. So we can look at a layer of rocks in any given place, and we can find
rocks disintegrate.
Well, they can, but a lot of rocks are preserved. If you start digging right outside your door, you'll find layer upon layer upon layer of rocks. And the soil that we have out there today, someday will be part of a rock layer. We just keep building stuff on top of it. It takes thousands upon thousands of years. So, things happen, rock layers get shifted and whatever else, and we end up with faults and folds. But we can go back, and this is the job of geologists, they can figure out how old those rock layers are. And there are other forms of chemical analysis, but there are also things like knowing when some event occurred. So you can figure out that, oh, this layer of rocks is 2.3 million years old. So then if you find a fossil in a 2.3 million year old piece of rock, guess how old that fossil organism is? 2.3 million years old, right. So this is the other part of how we tell how old stuff is.
What if our estimate's wrong?
In what way? Like in terms of aging rock?
Yeah.
We have pretty good science for that. So we have pretty good science for that. It's also, for some rock layers, it's also based on radioactive decay. So there are other forms of radioactive decay that don't affect living things, but do affect minerals. And so you can do that kind of chemical analysis. You can also look at other rock layers from around the world. So, and compare. Okay, when we put together a bunch of fossils, we can start to see changes over time.
Even with ourselves, like cavemen.
So when we look at a group of fossils, and this is a terrible drawing, but we can look at a group of fossils and say, oh, those things look related. But there are some subtle differences in them. So we can start to say, well, which ones look more closely related? Well, which one looks like it could have led to the next one? And, we can start to sort of trace a progression that shows how something evolved. In this one, the changes that we're supposed to be seeing, like I said, bad drawing, the head is getting larger, and at the same time, in each step of this process, we're seeing the tail sort of contracting. We're seeing fewer bony fins in the tail. So we're getting a bigger head from here to here, and we're getting a less complicated tail from here to here. Okay, so we can look at a series of organisms and say, oh yeah, this must come first. This must come next. It's a matter of recognizing patterns. So in whales, for example, and we talked a little bit about this, if we look at fossil ancestors of whales, you can actually see a real clear lineage. You can see a real clear line of relationships back to organisms that are land dwellers, and from there back to organisms that were aquatic. So it shows us those evolutionary stages, which is kind of cool. Okay, so we finished up. Our first source of evidence is fossil record, and that's our first one. Now we're going to talk about structural evidence for evolution. And I'm going to read this, then I'll shut up and let you copy, and then we'll talk about it. Structural evidence. Homologous structures show common ancestry. So one example is the bones of the human arm, the bat wing, the penguin flipper, and the alligator forelimb. The other piece of structural evidence is what's called a vestigial structure. Vestigial structures are considered to be evidence of an organism's evolutionary past. And examples include things like snake legs and whale legs. All right, so let me tell me if you have seen this graphic. That's the forearm of a group of animals. So a human, a cat, a lizard, a whale, a bat, a frog, and a bird. And what you're looking at, let me get rid of this, is homologous structures. So homo means what? Same. So these are the bones of the forearm of 7 different types of organisms. And not all of those are mammals either. So we've got the humans, the cats, the whales, and the bats are mammals. We've got a reptile, an amphibian, and a bird. And they all share the same bones. Now they're arranged differently. They're arranged slightly differently, but when you look at the structures, they're the same types of bones. It's the same number of bones in the case of mammals. Some of them are shortened, some of them are lengthened. So this is evidence, this is all vertebrates. This is one more piece of evidence that there's some common ancestor. Let's finish this up. We'll talk about vestigial structures tomorrow. But these homologous structures are evidence that all of these species radiated out from some shared ancestor. We'll also talk a little bit tomorrow about adaptive radiation and convergent evolution. So we'll finish.